Continuity. Okay, so this is what's going to be really important, is this definition of continuity. We're going to use this to prove continuity. So like whenever a question says justify, show, prove, etc., think about this definition. Because there's a way to see that something is continuous by looking at a graph and just being like, yes, it's continuous. Like, oh, look at that graph, it's continuous. It doesn't have any breaks in it, no holes or jumps or asymptotes. But it's a lot harder when we just have an equation and when we have to prove it. And so that becomes really important. So the definition is 3 parts. And depending on the function, we might need to think about all 3 of these, but the most important part is part 3. If we can show that part 3 is true, then we've proven that something is continuous. And what part 3 says here, in normal words, is that the limit of f of x equals the y coordinate of f of x. And so if we can show that, then we can prove that something's continuous. The other parts to say that f of c is defined, that just means like the function has a y coordinate. At x equals c, that's what we're talking about. Some random x value. And number 2 is saying like if the limit from the left equals the limit from the right. That's another way of saying that the limit exists. And so then a function being continuous means like the limit and the y coordinate are the same thing. So I want you guys to see if you can do this here, because I bet you can. I want you to sketch 3 different graphs here. Condition 1, is talking about number 1 in the rules there. But see if you can sketch a graph where like condition 1 is true, but number 2 doesn't hold, vice versa, and then see if you can do, see if you can do all this so you can read it. Sketch a graph. Okay, let's talk about these. So we'll just call these 1, 2, and 3. For which one of these do we have a hole in the graph? 2? Yeah, so we have the limit from the left and the right exists, but there's no y coordinate. Are there any others that have a hole in the graph? Drew, what do you think? Is there another one with a hole in the graph? The first one, that's not a hole in it. Your drawings are right. I can see your drawings. Yeah. So the third one also has a hole in the graph. The difference between 2 and 3 is, number 2, like it says condition 1 does not hold, so there's no y coordinate. For the third one here, conditions 1 and 2 are true, so there is a y-coordinate and the limit exists. They're just not the same thing. So there's a hole and a floating point right there. So there's holes in both of those. So then what do we have in example 1? What kind of discontinuity am I drawing here? A jump, yes. And for condition 1 to be true, what would I need to add to that drawing right there?
Fill in one of the circles.
Yeah, exactly. I just need a closed circle so that we have a y-coordinate. Okay. So, when we need to show that a function is continuous at x equals 1. So first of all, show that the following function is continuous. So right now we know the answer of the question. Is this function continuous at x equals 1? Based on the wording of the question.
Yes.
Yes, we do. Show that it is continuous. Okay. So if we get a different result, either there's a typo in the problem, or we've done something wrong. So we just need to know that ahead of time. So since it says show, we need to think about the definition. And it's at x equals 1, so when we're showing the limit as x approaches 1, am I going to have to split this into left and right hand limits?
Yes.
Yes, I am, because 1 is where the function changes. Okay, so here's the best and most efficient way to show this, is we just say, so let's say we have the limit of f of x as x approaches 1 from the left. So which of these would be left, the top or the bottom? Top, yeah. Yeah, because that's x less than 1, so 2 times 1 minus 3 equals negative 1. Okay. Then the limit as x approaches 1 from the right would be the other function. So natural log of 1 minus e to the 0. What is natural log of 1?
Zero.
Yes, natural log of 1 is 0. What's e to the 0? 1. So that's negative 1. Okay. In doing this limit right here, we also found what part of the definition that we need? We need to show that the limit and the y-coordinate are the same thing. So which part did we show just now? Yeah, we showed that the limit exists. Where would I plug 1 in to get the y-coordinate? The bottom one, right? But we just did that. So that's also the y-coordinate. Okay. So these two numbers are equal, right? So we can put an equal sign right there. And it doesn't matter where we do this. You can do it on either side. But that's also the y-coordinate. So we're done. That's it. We've shown that the function is continuous at x equals 1. And we can do it all just in one step like that. Limit from the left, limit from the right. So then the only difference here is when we say, is the following function continuous at x equals 3? So notice, like, same deal, 3 is where the function's changing. When we do the limit from the left, That's the top function. 3 squared minus 5 is 4. From the right, nine minus 2 times 3. So that's 3. Okay. So these things are not equal, which means that this function is not continuous because the limit doesn't exist. But this work here is the reason. So notice like I just left a little space right there, and I could either put an equal sign like we did in the last one, or I could put a not equal sign because they're not equal. So we can just say no because, and we have this. The limit from the right does not equal the limit from the left. That's all we need to say. So it's like we're thinking about that 3-part definition, but like we're showing whatever part of it we need to show.
Are we just allowed to just say no, or do we have to say no because? Like if we show the work, can we just say no?
Yeah, that's fine. Yeah. Yeah. But like that's our reason. So we don't need to write anything. We don't need a sentence or a paragraph or anything. Okay. Turn to your neighbor. How are we going to do example 4? Talk about it. Okay, we've done problems like this before, very similar to some of these other problems we've done. What are we going to need to do here?
Cry.
After we cry. We can cry first. That's okay. Then what? We're trying to make this function continuous. What do we do?
Solve for C.
Solve for C. How do we solve for C?
Set the equations to equal each other.
Okay. Set the equations equal. And like this, cx squared minus 2x equals 5 plus c. Okay. Is this always true? This statement here?
Well, in this case, yeah.
Uh-huh. Can we assume that this is true for all values of x?
No.
Okay. Where do we want to make these functions equal each other? At x equals 3. So you got to be careful because this is not always true. This is only true at x equals 3. Because when x equals another number, c could still be the same thing, but these functions are just doing totally different things here. So it's okay to write this if you say at x equals 3, and that's okay. So you can write that. But if that's missing, actually technically you've written a false statement, and that's something that gets more relevant next year in calculus. If you write things that are not true, like you lose points. So that's an okay statement because that's a true statement. Or you can just plug 3 in for x, and so you could say like c times 3 squared minus 2 times 3 equals 5 plus c. That's usually how I vote doing it, because a lot of people forget about that. So we're plugging 3 in for x and setting them equal. So we have like 9c minus 6 equals 5 plus c. And so now we can just solve for c. We get 11 over 8. Did I do that right? Okay. Gross. Okay, so since this is the right side and that's the left side, we're making sure this graph meets up That also accounts for the closed circle. We don't need limit notation with this, like this is fine, the way that is written. Okay, so just a few more things about discontinuities here. Discontinuities fall into two categories: removable and non-removable. Bless you. So when we're talking about non-removable discontinuities, this is our jump and our vertical asymptote. And when we say removable, we're talking about a hole in the graph. Okay, we've talked about these things a lot. I want you guys to see if you can come up with an equation that would create a jump, a vertical asymptote, and hole. You don't have to sketch a graph of that equation. You can just sketch a graph of that discontinuity in general. So they don't have to match each other. Okay. For a jump discontinuity, what kind of equation are we going to have? Yeah. It's going to have to be a piecewise equation. It's the only way we can have a jump discontinuity. Okay, so we could say, I mean, what needs to be true for it to be a jump? We need an x value, right? What x value do you guys want to choose? 3, okay. So we need like an x greater than or equal to 3 and an x less than 3. So to have a jump, it means when we plug 3 in, we're going to get what for the two equations? For there to be a jump.
Different numbers?
Yeah, different numbers. Okay. So as long as they're different at x equals 3, we're good. So like, don't do x squared and 3x. This function's continuous. But 3x plus 1, is that going to work? Yeah. Or even, I mean, I'm making it complicated here. What about like 1 and 2? Is that going to work? Just y equals 1 and y equals 2? Yeah. Anything that makes two different y values when we plug 3 in. And if I graphed my function, which you don't have to, but if I just graphed mine, there's 1, there's 2. So here's 1, 2, 3. Oops. So closed circle going that way, open circle going that way. Okay. Real simple. But you could draw anything for that, just anything with a jump discontinuity. For a vertical asymptote, what are we going to see in our equation? What makes a vertical asymptote?
Something canceling out.
Something canceling out? That is not for a vertical asymptote.
That's a hole.
Yeah, that's for a hole. So if we saw something cancel, what do we want to cancel? What are some things that could cancel for a hole?
X minus 1.
Yeah. So we have like x minus 1 on the top and bottom. And then we just need like one other thing. X plus 2. We don't even need anything on the bottom. So this would be the line like x plus 2. It's got a hole at 1. For a vertical asymptote, what would we need? Okay.
Something on the bottom that doesn't cross out.
Okay. Yeah, like what?
I like x minus
Yeah. Sweet. Yeah, as long as it doesn't cross off. So where's our asymptote going to be?
5.
Yep. Nice. It's all the same stuff from, or especially these two. All the same stuff from Unit 2. Graphing these rational functions. So if it crosses off, it's a hole. Doesn't cross off on the bottom, it's an asymptote. Jump discontinuity, we need a piecewise function. Which seems to not be equal. Okay.
Could you have a piecewise for a hole?
Yes, you can have a piecewise function that has a hole or a piecewise function that has a vertical asymptote. Yeah, absolutely. So if I had something like f of x equals, let's say, 1 over x for x greater than -1. This is going to have a vertical asymptote at x equals 0. And then maybe I have like x squared minus 9, x plus 3 for x less than or equal to -1. This one's going to hole at -3. And it also probably has a jump discontinuity, I would guess. Yeah, it has a jump discontinuity. So, yeah, this one's got all of them. Yeah. Okay, let's go to the next page here. I want you guys to do examples 4 and 5. These are really similar to the ones we did on the front of the page. For number 4, remember we want to label the left-hand limit and the right-hand limit, and also the y-coordinate, f of 2. Since the left and right equaled each other, I can just put an equal sign between them. I actually do want you guys to say this. Yes, f of x is continuous at x equals 2. Make sure you have a sentence there. So I should have said that earlier. That's my bad. And notice how my work's a little spread out. Like I just wrote 10 minus 7 over here. But then I still had this equals 3. So I just didn't finish writing it. And that's okay. If it's all equal, it's all good. I see that it equals 3 right there. For example 5, we don't need the limit notation. We can just set the two halves equal to each other with 1 plugged in for x. But we can use the limit notation if we want. If we wanted to put it in, optional, this would be x approaching 1 from the left. Or this is q of x, not f of x. Q of x. And this is the right-hand side. So if you put it in, just make sure they're labeled correctly. But you don't need to put it in. But we get c equals 2. Okay. Any questions on that? Okay.